I'm cryptax. I'm really happy to be with you, and we are going together to crack Rust with the help of artificial intelligence. And this up there is Pico le Croco. He's like our companion for this presentation. Usually what he says is pretty useless, to be honest. But let's get started. So to discuss with artificial intelligence, we'll use a Radar2 plugin, which is called r2ai. In this presentation, we are going to have two different stages. One, where I show you how to install r2ai, and then after that, how to crack a Rust program. Okay? So, let's install it. We have to clone the repository, github.com, radar.org, r2ai. We go in the repository, and actually the plugin we are looking for is in source. There's another interesting plugin, Decay, which is very similar to r2ai, except it's implemented in JavaScript, and this one in source is in C. So I'll go there, make user install, and we're done. Okay, by the way, if you do not want to compile your plugin, you can also do it like that. Well, you initialize r2pm, then, for instance, we can install Decay, and we could have done the same for r2ai, okay? The only difference, or I'd say with compiling, is that, well, if you're using a plugin from the package manager and you have, I don't know, an old R2 but you're using a recent plugin, you might have a version mismatch. Now, the other thing we need is API keys for our LLMs. So you have to put your API keys in files in your home directory, and you see here I have 3 different files from different providers. Anthropic is a paid API key. The other 2 give me access to free models. We're going to use very much today a Grok, okay? But you just copy paste your API key in there. I'm not going to show you the content of my files, but that's just what you need to do. So now r2ai. I'm going to go in the workshop directory, and we have one binary. And, well, there we go. We need to enter the docking authorization code. It's basically just a binary about, the authorization code for a rocket. So, I don't know, let's try Pico le Croco. And now authorization failed. That is not the correct password. And so all the goal of this presentation is for us to crack this binary and find the correct authorization code that we must find. So let's reverse this binary. In R2, the first thing we are going to do is we are going to analyze the binary. There we go. Okay, and now, to be honest, this binary is extremely simple. It's just 24 lines of code, so nothing really complicated. But if you don't know Rust, or if you don't know what the Rust compiler does, you are going to find this significantly difficult. Just have a look at the numbers, the number of functions which have been generated. 620 functions generated for my poor 24 lines of code. Okay, so this is going to be a little bit difficult, and unless you are really experienced at reversing Rust, I think you will find that some help from artificial intelligence is going to be quite useful. So can you actually locate the main of this Rust binary? It's not that obvious if you're not used to reversing Rust binaries. The first thing we're going to do is IE to locate the entry point. Okay, so now we go in here and we disassemble. We see obviously it's calling the main. Okay, here we go in the main and we disassemble again. Now, well, either you see that it's obviously calling here this function, which looks really interesting and looks like the main part that I am looking for, or you don't, and we are going to pretend you didn't see it and that you need a little tip from the artificial intelligence. So to do that, we are going to ask a direct question with option D to our LLM. Now, first of all, I need to configure which provider I am going to use. So Grok, and for the model, often the names are long. I'm going to use, well, this one. Okay, GPT OSS is honestly not the best choice, okay, because it's more kind of a generic model. It's better for reverse engineering to use something which is more like for code. But this one is well known and it's going to be a very simple question, so we'll start off with that one. So -D, where is the main of my Rust program? And yeah, it tells us it's in here. Okay, so we're quite happy with that. So this is the direct mode, okay, and by direct it means that we only have one request and one answer from the LLM on the other way. You can actually view the requests. They are stored in the TMP directory, r2ai OpenAI request. And we see here our context, which is sent to the LLM. This part is filled in by r2ai automatically, and this is our question, and it also sends the disassembly of the function. And then we can view the response also that way, where you see, well, the answer of the LLM. So, okay, we know that our function is here. We are going to go there. We ask to disassemble it, and we get all this code, pretty lengthy. Okay. And now we are going to ask the LLM to decompile that. Now, to make it look a little bit more kind of real, this was coded, implemented in Rust. We are going to ask the LLM to give us Rust as output. That's the way to do it. And then to do the decompilation of the current function, it's just the D option with no trailing question. And we get that. Now, to be honest, this result isn't that good. Okay, there are plenty of things which are kind of a little bit wrong, and I'm going to switch to another model. Okay, and let me try rather this one. Kimi K2 Instruct is hopefully going to give us something slightly better. And yes, it's far better than that. Okay, so apparently there is a secret string, which is this one. Then we just ask enter docking authorization code. We read the input, and we check that well, our input matches the secret. So normally our secret, our docking authorization code should be that, right? And we'll run it, and the authorization code is apparently this one. Let's try that. Access denied. This is not what we, the code we are looking for. It's incorrect. Okay? Okay, so we're going to try and find out what is happening, and to do that we are going to use the other mode that we can have in r2ai, which is the automatic mode. Now, the automatic mode is extremely powerful because it allows the LLM to use tools that you have on your host. And with the automatic mode in r2ai, you are allowing the LLM to use your radar 2 and also to execute JavaScript programs. Now, you might be a little bit scared, and you are right too, but we will see how we can approve, disapprove, or modify what the LLM wants us to run on our host. Now, I know that everybody, or nearly, is going to start their automatic mode with this type of question, like, give me the solution. This is CrackMe. Give me the correct authorization code. Now, be warned, this is a bad idea. I'm going to do it just to show you, but it's a bad idea because actually this is a Rust program. There aren't that many resources online about how to deal with Rust binaries and their assembly, okay? So the LLM is going to struggle, and it probably won't be able to find the solution just like that in a snap, okay? You should rather work out the solution on your side and ask the LLM for more precise and smaller steps. Okay, we'll try that nevertheless. So along with our question, we can send the result of an r2 command. I want to send something which is not too big. Listing all the functions is far too long, so I'm going to reduce it there. So here, this is what the LLM is asking. It wants to analyze the binary and to start by having a look at the main function. So it's doing that. If you know R2, you know that this is not going to be totally enough. If you want actually to see the instructions, at least put PDC afterwards. And it continues. It says, okay, let me have a look at string comparisons and look for the expected authorization code. Okay, I know this is going to fail, but well, I think it is. So we see the various strings, enter docking authorization code, etc. Let me look at the string that is being compared against user input. So 57D30, what is that? And here we are encountering the specific 429 response code, which basically means that, well, you are going too fast, okay, and you just have to wait a little bit. Actually here, what is happening is that it's trying to view this string, okay, but it doesn't know how Rust works. Okay, so here actually we see one problem the LLM is facing is that it doesn't know about fat pointers in Rust. In Rust, you don't have directly the string at a given address, but you have a pointer to the pointer of the content and the length of it. So we're going to interrupt this flow because it's never going to manage to go to the response. And we are going to have a look at this address ourselves to investigate a little bit. And indeed, we see the length of the string here and the pointer to the data in here. So if we do something like that, and 040489E1, well, we get our first string, enter docking authorization code. Work out the correct authorization for this CrackMe. Okay. I'm completing because it wants the disassembly for it. Okay, interesting. It wants to map this, okay, to characters. Why not? Okay, so this is actually, it's a JavaScript, so it's going to run this JavaScript program. This is not malicious, so okay, go on, and we can see the values in here, E, P, D, L, P, S, etc. Let me check the actual values. Okay. Okay. The code is creating an array with values and then calling ita, map, and collect to transform it into a string. Let me check what the password is by looking at the comparison. Okay, this looks good. So yeah, we see here that we have our comparison, okay? And we are comparing, so it's compare, partial, equal, something like that. We are comparing two variables, var a0 and var 110. Okay, so probably it will need to work out what these are. Let me check the actual string data that's referenced in the code. I see a reference to enter docking authorization code. This, I think, is not going to work, but we can let it try. Yeah. Now it looks like it worked out here, the string. Nice. So it's already tried this a couple of times. This is not going to work. I'm going to stop and have it do something else. Okay, so if we have a look at the list of context that we have it here. We can see, well, a little bit better. Is there a place where we can get, yeah, the strings in here? So E, P, D, L, P, etc. We're going to try this one on our program. There we go. So, is this going to work or not? Well, no, this is not the correct authorization code, as kind of expected, because it's really kind of a random string. But nevertheless, if we have a look at our function, well, we see that the string is somewhere here, E, P, D, L, etc. And then it goes indeed in a slice, then it goes into map, then it goes into collect. Okay, so this is not like a total hallucination. This string is there. And we also saw some other place in the analysis that it did that we are doing a comparison, a string comparison, PDF CMP. So there it is, string comparison. Let me disassemble a little bit before that place. And we see that it is taking two arguments, var a0h and var 110h. So what are these? Let's investigate a little bit more. So we see that var 110h is from RCX, and RCX is from var 18, and var 18 is from RAX, and RAX is the register where you put the result of a function. And so this is going to be the result of trim. So actually this is the trimmed input that we have. Let me try and decompile that. I'll specify Rust in case it's no longer there. And So you see, we read the input from the user and we trim it, and we are comparing this, well, maybe not exactly with secrets, but we are comparing it with var a0h. So what is var a0h? We can search for it that way. And we see it is used in those locations. Let's have a look, for instance, at 20 bytes around this place. I don't know, something like that. And we see indeed var a0h, which is an argument to collect. Oh, interesting. Okay, so the string we are comparing to, so here it says that we're doing that. It's not showing the fact that it's calling collect and map. So maybe we can do it like that. The function is calling map and collect. Please show the correct decompiled code. Okay, so we see it really better here. We see that it's calling iter, it's calling map with here a closure and then collect. So we are comparing here our input with the argument which is provided to collect. Interesting. So let's recap a little bit. We have this string. We know it is created at the beginning of the main. We know it is not the solution to our CrackMe. Okay. We know that we have a string comparison by the end of the CrackMe, and the one part of the comparison is made on the trimmed input user input, and the other part is var a0h is actually an argument to collect. So some string passed here to collect. Okay. The other thing is look at what the LLM told us here. So this string appears to be the Caesar shifted version of docking code, each letter shifted by one position in the alphabet. So is this true? If we take E, and we shift by one back, yes, that's D. P, O, D, C, L, K. So we have doc, but P, capital P, is not I. Okay, so a little bit strange. Let's have a look on CyberChef. I'm gonna put this one in there. We're going to rotate, but it's -1. And we get here doc origin. It's just that little last character is not shifted up. I don't know how to fix that. So we'll go to the ASCII table, and we see here the column here, and just before that is 9. So our code should be doc origin 9. That looks like a little bit real because, well, you know, it's kind of readable, right? So, well, let's try that. And here, doc origin. So doc origin, capital, and 9. Yes. Docking sequence authorized. Welcome aboard. So now this seems a little bit kind of lucky, you know, because, well, we got the code, but we don't exactly know in our code who and which part is transforming this secret encoded string into doc orient 9. So where could that happen? Well, it's gonna happen probably something there because it's saying it's transforming it. And this there is something we need to discuss. This is a closure. So let me explain a little bit what the Rust compiler does when it sees a closure. Right. So imagine that you have this piece of code, okay? The closure is in here, add x. It's basically a function that captures a given environment. In this case, the environment is x, where x equals 5. So that when we call our closure over the argument 3, well, it does 5 plus 3 and returns 8. Well, now, when the compiler sees this closure, it is actually going to create a function and to monomorphize the closure. And now, to understand what that is, I'm going to go back to monomorphism. There we go. I'm sure that you know what polymorphism is. Polymorphism, it's a function which can be used over several different types. Monomorphism is kind of the opposite, not quite. It's the concept where you are going actually to generate one function for each type that your sort of generic function is meant to work on. This is usually done for optimization reasons, right? So let's have this example where we have a square function in Rust, which is generic, okay? And it actually can run over integers and floats. Well, when the Rust compiler sees that, actually it is going to generate one square function for integers and another square function for floats. Okay, so you'll have two. Now, this happens, this same concept, monomorphism, happens quite often for closures. You will have like a very special function that the Rust compiler generates for your closure, right? And if your closure is sort of generic, is meant to be working on floats, on integers and everything, the Rust compiler is going to generate a function, function for the closure for integers and another one for floats. And then the call will happen this way. You will actually set as first argument, actually the environment of the closure. So here, for instance, it was x. And then the second argument is going to be the sort of real argument for the closure. So it's 3 in this case there. Okay. So this is pretty important, and do remember, especially if you are like me coming from a Seek background, when you don't understand where things are happening, okay, there's no magic. It usually is happening in the closures, and closures are really important in Rust, in Dart, and some other languages. Don't forget to check them out. So let's go back a little bit to R2. We know that something is probably happening over there. How about we have a look at closures, okay? So we can actually list like that and search for closures, but we have lots of closures, okay? So let's find one which is for our main. Actually, we can see it directly there. This one, okay? This is a closure inside the main of our doc code. You can also find it a little bit better like that. Interesting. Let's go in here and let's decompile it. Let's say we need perhaps a little bit of help from the AI. Okay, decompile that. It is actually doing this. This is not extremely clear. Maybe I can get some explanation with -x. decrements. So, okay, this didn't work out exactly as it should. It really depends sometimes to understand that the way providers or model work. Okay, but it tells us decrements the first argument by 1, ignoring the second. Okay, so we are indeed here decrementing by 1 the string that we provide, which is like this one. So we are indeed decrementing this over there. Okay, so to recap, we installed r2ai. Then we used it over a CrackMe binary, which was implemented in Rust. We configured r2ai to use a free API key that we have from Grok. And then from there, we used the direct mode to get the decompiled version of the main, which helped us out. It was not fully correct, but it helped us out to understand what was happening a little bit. We used the automatic mode also to get some better insight. And after, well, helping the AI or helping ourselves, we managed to understand that there was a transformation on a fixed string, which was at the beginning of the main. And we found this transformation and we found the correct authorization code. Thank you very much for listening, and bye-bye.